Dear students, now let us study the module 4 Nano Materials and Characterization Techniques. Now, introduction to the nanotechnology or nanomaterials. Nanomaterials are cornerstones of nanoscience and nanotechnology. Nanostructure science and technology is a broad and interdisciplinary area of research and development activity that has been growing explosively worldwide in the past few years. It has a potential for revolutionizing the way in which materials and products are characterized and the range and the nature of the formalities or functionalities that can be accessed. It's already having a significant commercial impact, which will surely increase in the future. Nanoscale materials are defined as a set of substances where least one dimension is less than approximately 100 nanometers. A nanometer is one millionth of a millimeter, approximately 1 lakh times smaller than the diameter of human hairs. Nanomaterials are of interest because at this scale, unique optical, magnetic, electrical, and other properties emerge. These emergent properties have the potential for great impacts in electronics, medicine, and other fields. Now, the importance of nanotechnology. Nanomaterials have created a high interest in recent years by virtue of their unusual mechanical, electrical, optical, and magnetic properties. Some examples are given below. Nanophase ceramics are of particular interest because they are more ductile and elevated temperatures as compared to the coarse-grained ceramics. Nanostructures or semiconductors are known to show various nonlinear optical properties. Semiconductors' Q properties also show quantum confinement effects, which may lead to special properties like luminescence in silicon powders and silicon germination quantum dots as infrared optoelectronic devices. Nanostructures semiconductors are used as window layers in solar cells. Nano-sized metallic powders have been used for the production of gas-tight materials, dense parts, and previous coatings. Cold welding properties combined with the ductility make them suitable for metal bonding, especially in the electronic industries. Single motorized magnetic particles or nanodomains and aspects that also in the magnetic nanophase materials, the grains correspond with the domains, while boundaries on the contrary to disordered wall. Very small particles have a special atomic structure with a discrete electronic states, which give rise to special properties in addition to the supermagnetism behavior. Nanostructure metal clusters and colloids of mono or plurimetallic composition have a special impact in catalytic applications. They may serve as precursors for few types of heterogeneous catalysts and have been shown to offer substantial advantages concerning activity, selectively, and lifetime in the transformation and electrocatalytic. Nanostructure, nanometal oxides, thin films are receiving a growing attention for the realization of gas sensors with enhanced selectivity, sensitivity also. Nanostructure metal oxides finds application in rechargeable batteries for cars, consumers, goods, monocrystalline silicon films for highly transparent contact thin films in solar cells, and nanostructure enhancement leading to the strong absorption in dye sensitized solar cells. Now, the emergence of nanotechnology. The term nanotechnology was first used by Japanese scientist Noriyuno Taniguchi in the year 1974. Paper on production technology that creates objects and features on the order of a nanometer. The modern history of nanotechnology began in 1959 when Richard Feynman, a Nobel Prize winning physicist, delivered a speech titled "There is a plenty of room at the bottom." In his speech, Feynman discussed the importance of manipulating and controlling things on a smaller scale, saying that the principle of physics, as far as I can say, do not speak against the possibilities of maneuvering things atom by atom. Now, the bottom up and top to down approach. The first one is bottom up approach. What it is? These approaches include the manufacturing of materials, components, with further self-assembly process leading to formation. During self-assembly, the physical forces operating on a nanoscale are used to combine basic units into larger suitable structures or stable structures. Typical examples are quantum dot formation during experimental growth and formation of nanoparticles from colloidal dispersion. Nanomaterials are synthesized by assembling the atoms together instead of taking material away to make structure. Bottom-up approach selectively adds atom to create structures. For example, plasma etching, chemical vapor disposition. Now the second one is top-to-down approach. These approaches use larger initial structures which can be externally controlled in the processing of nanostructures. Typical examples are etching through the mask, ball milling, and the application of severe plastic deformation. Nanomaterials are synthesized by breaking down of bulk solids into nanosize. Top-down processing has been and will be in the dominant process in semiconductor manufacturing. For example, ball milling, sol gel, and lithography techniques. Now, the challenges faced in the nanotechnology. The challenges are arising from the nanotechnology is largely on target. No single person can provide the answers to the challenges that bring nanotechnology, nor can any single group or intellectual discipline. However, those who know the technology best must ultimately prepare the agenda for broad discussion. There are 5 main challenges in the nanotechnology field. The emergence of nanotechnology, we feel that there is a very real need to minor exposure to human hair in the humans in the air and within water. The challenge becomes increasingly difficult in more complex matrices like food. The second challenge would be to develop and validate methods to evaluate toxicity of engineered nanomaterials within the next 5 to 15 years. The third challenge is to develop models for predicting the potential impact of engineered nanomaterials on the environment and human health. The fourth challenge is the next challenge would be to develop reverse systems to evaluate impact on the environment and health impacts of engineered and nanomaterials over the entire lifespan, which speaks of the life cycle issues. The last challenge is to develop the tools to properly assess risk of human health and to the environment. Thank you.